Good evening. Welcome to this very special session of Astro Adda, where we will be celebrating more than 5 decades of existence of an iconic facility for radio astronomy, and very recently there was this very poignant incident of the structure collapse, and we are wishing to bring to all of you, school and college students, an idea of the the kind of unprecedented radio astronomy results which had come out from that, and none better to bring to us than our speakers today, who have had decades of experience as astronomers at the observatory, and who for whom the telescope is a family member. And to introduce our speakers and to preside over the session today, I would like to invite Professor Jairam Chengalur, Senior Professor and Dean at National Center for Radio Astrophysics, which operates the Giant Meter Wave Radio Telescope. India has a strong footprint in radio astronomy, and it is important for us to get a worldview of this. And I would invite Professor Jairam Chengalur to please take over as chair and preside over the session. Introduce our speakers. You are muted. You are muted.
Yeah, thank you, Ratnashri. And, it is a great privilege to be here with all of you all today to, commemorate, the achievements of what Ratnashri rightly called actually an iconic radio telescope, a radio telescope which has really done, path-breaking things over all of its decades of existence. And as Ratnashri said, we are very fortunate to have with us today two people who have been, very intimately connected with this telescope for many, many decades, Chris Salter and Tapasi Ghosh. And, it's somewhat early in the morning for them today, and I do appreciate their, sort of making the effort to be here with us today and to share with us, some of their, share with us this summary of what all wonderful things the telescope has been doing. So with that, maybe I'll just give a formal introduction to both Chris and Salter. And it is, as I said, a pleasure to introduce them both. I've known them for many decades now. I first met Tapasi at the Radio Astronomy Center in Ooty in the early 1980s when I myself was a summer student and Tapasi was a graduate student. I met Chris a few years later. As I recall, Tapasi gave us summer students lectures in radio astronomy, and these were, in fact, probably my very first lectures on this topic. One of the things which many of the students may not appreciate and which I did want to draw out is that most, many, if not most of the radio astronomers today are based at universities or research institutions, and they almost rarely actually even see a telescope, let alone, do anything hands-on with a telescope. Instead, they just get their data over the internet. And in contrast to this, both Chris and Tapasi have spent their professional careers at radio telescopes. And they're, one of a few of a vanishing breed, what I would call, true radio astronomers. People who lead this kind of nomadic existence working at radio telescopes all over the world. Tapasi herself got her BSc and MSc in physics from Calcutta University, and then she joined the Indian Institute of Science in Bangalore as part of the joint astronomy program. She was just the second batch of that program. That program is still continuing. It's been a very successful program, and it's also a very interesting one. Many institutions in and around Bangalore got together to run this program. So the courses are taught by faculty from many institutions, and the students have a choice of working at any one of these institutions for their PhD. And it's produced a very large number of outstanding astronomers over the years. Tapasi's PhD itself was based on observational work from the Ooty Radio Telescope, built and operated by TIFR, and she worked with Pramesh Rao and Gopal Krishna. Following this, she did a postdoc in the Netherlands, working primarily with the Westbroek radio telescope, a major radio facility in Europe, working with another stalwart of radio astronomy, Claire de Browne. Following this, she moved to Arecibo Observatory, where she worked for more than 25 years, and until very, very recently. And in 2018, she'd moved to the Green Bank Observatory in West Virginia, which is the largest steerable parabolic dish in the world. At Arecibo, Tapasi played a major role in testing and commissioning a lot of new equipment, helping users get the best out of the telescope, and also in working on technical aspects of what is called very long baseline interferometry. So this is a kind of experiment where you combine data from telescopes spread across the globe to make very, very high resolution images of the sky. Tapashi's own interests are in extragalactic radio astronomy and in molecules in external galaxies. Chris got his PhD from the University of Manchester, he got his MSc and BSc from the University of Manchester, followed by a PhD at Jodrell Bank, working with Glenn Haslam on radio continuum emission from our galaxy. And following this, he moved to the University of Bologna in Italy. And then after a hiatus of about 5 years, he joined the Max Planck Institute for Radio Astronomy in Germany. The hiatus was to take care of family responsibility, and Chris was working as a research and statistics officer at the Dakarum District Council, and where I understand that his primary responsibility was to design housing estates. So that's probably about as far from radio astronomy as one can get. But after a hiatus of 5 years, Chris was back, and after that, he had a truly nomadic life. Counting through the places he's been at, I got close to 10 radio telescopes around the world where Chris has worked, including a stint with TIFR's radio astronomy group at UT. The longest stretch of time, however, was at Arecibo, which is what we'll hear about today. Chris retired as an adjunct professor from Cornell University in 2018 and is currently an emeritus scientist at the Green Bank Observatory. He's also a dedicated sports fan, and one of the things that I do remember is his long ball-by-ball cricket commentary that he used to send by friends over email in the late 80s and the early 90s. At that time, I myself was at Arecibo Observatory, and Chris's emails were pretty much my only reminder about the existence of cricket in the world. And, interestingly, I think probably sports has been one of the constants in Chris's life, although his affiliation to radio telescopes has changed over the years. One thing which has remained unchanged is his devotion to the Watford Football Club, of which he's been a lifelong supporter. So with that, I'll hand over to Chris and Tapasi. Yeah, please.
Thank you, Jairam. And I will add your presentation. Momentarily, it will show a little bit screen within screen. When I put your presentation in full screen mode, I would not be able to see in the studio. If there is any problem with the presentation, I'll be able to hear if you say it. So I'm just adding it.
Lovely. I guess at this point we take over on a extremely cold. It's about -3 degrees centigrade outside our front door at the moment here in West Virginia. I'm sure it's a lot warmer in Delhi. Anyway, could we move to the first slide, please, Ratna?
Yeah. Is it not visible, the first slide?
Yeah, that's the title
sorry,
page.
the next slide, should I say.
Oh, next slide. Yes.
Thank you. Just in case some of you don't know where Puerto Rico is, it's in fact an island in the Caribbean, in the West Indies. I should say, after Jairam's lovely introduction, the non-cricket playing part of the West Indies. It's one of the larger islands in the Caribbean. And if you look down on the island from space, you'll see a small, or you would have seen until December of last year, a small circular object in the middle of the island, which is the observatory with the Arecibo telescope nestling in the karst hills. And if you came in even closer, you would see it was a telescope, and then you would see its structure. But let's go back 57, a little more, 60 years to when the original idea came. Next slide, please. Here is the original paper where a gentleman, Professor Bill Gordon, who was at the University of Cornell University, thought big. And he was a studier of our ionosphere, the Earth's ionosphere, and he wanted to detect coherent backscatter of radio waves from the electrons in the ionosphere. And he worked out that you would need a 300-meter diameter dish to do this, and proposed that this could be built as a single fixed antenna. And he proposed hanging this great big spherical dish inside a sinkhole somewhere near the equator. And it was an unthinkable idea in 1958 when he proposed it. And he managed to sell the idea to the American Department of Defense. And he looked around, found 10 possible sinkholes. He liked particularly, if we could have the next slide, please, one he found in Puerto Rico, which had the advantage of being an American protectorate. It was not quite on the equator, it's at 18 degrees latitude, but it's fairly near to the magnetic equator, which is what interests an atmospheric physicist. It also means that the planets pass overhead, so planetary radar astronomers would be interested that they could bounce radio waves off the planets using this huge dish. And astronomers, he thought, would be interested, how true, and use the dish when it was not being used by the other two disciplines to do radio astronomy. And in fact, it's always remained that way. It serves three scientific communities: astronomers, aeronomers, as we call the people who study the atmosphere, and radar astronomers, and has remained such ever since. You could look at the next slide, please. That is how the sinkhole itself looked like in 1960. It was a tobacco farm, and it was taken over. The surface of the dish was made as spherical. The surface of the sinkhole was made as spherical as possible, and that is when construction began on what was to be, for the next 50 years, the world's largest single telescope. Next slide, please, Ratna, and I will hand over to Tapasi.
Okay, so in these slides, there are some snapshots of the original building. So we go clockwise from the top left-hand corner. That was in an office that was in Arecibo town. And you see Bill Gordon facing us, and his chief engineer, Mr. Domingo Albino, a Puerto Rican engineer. They're both at that time basically deep into designing. Then then you see the sinkhole needed to be shaped a little bit. It was almost spherical, but in places it needed shaping a little bit. And then the construction's coming on, and sorry, we are having problem looking at the pictures here. But anyway, and the construction, as you see there, the platform and basically the huge dish stays on the ground. The dish doesn't move. Normally in a radio telescope, the whole dish moves and thereby you point, but this is so big, it was difficult to move the dish around. So the dish basically stayed in the sinkhole, and receiving systems were hung from three big tower into a structure that was called a platform. It was a huge structure, very stable. It was like a bridge hung from three huge towers. And on the middle picture and the bottom row, you see there's a there's a bridge, just a very beginning of the bridge made. People were walking up at that time that way. And you see a bow-like structure. That bow is called the azimuth arm, and we'll explain more how this movement happens. This azimuth arm is attached to a circular ring, so the whole bow-like arm moves around a circular ring, and there were receiving antennas hung from the bottom of the bow out of two housings, which we call carriage house at that time. So those houses were on rails. They could ride up and down along the bow structure. So that's how we could cover part of the sky. We could look from the straight up, which is zenith, from zenith to about 20 degree on either side, and then we could move the entire arm around 360 degree. That's how a point in the sky within a cone of about plus minus 20 degree could be seen. So it was like a fisheye view, and it took about 3 years to build. And on the bottom left corner, you see the opening, the dedication of the telescope. First, it was built with a record time within 3 years, and with about $10 million. And the governor of Puerto Rico at that time, a very honored man called Dr. Munoz Marin, he is opening the telescope at that time. Next slide, please. Okay, so here is the final telescope as it was now. And as I was explaining, there are three towers there, and the dish sits on the ground, and you can see through. The dish is actually hanging from support structure around the rim road, so it's not touching the ground, it's not sitting on the ground. You can drive under the dish, and there are equipments down there too, various equipments. So that's the whole picture. Oh, one question, Ratnasri, can you all see these pictures, or do they look very dark for you?
They're somewhat dark, the question.
They're clear?
Yeah, yeah.
No, they are
Yeah,
little.
they're a little dark. They're a little dark.
Uh,
Yes, they're a little dark. I'll.
better to switch to the other one then, because I think
Uh, I have a few, but I don't have from very earlier times. I have one image. If I put it over this, flash it. No, okay, sorry. Uh, I'll. You wanted to talk about the? Can
yes,
you see the images I am flashing in the studio? Would you? Sorry. Did you want a closer look at the receiver? I'm flashing a few images in the studio, and I'll go back to the presentation now. Uh,
the PDF document you're showing.
oh, you want me to? No, no. So far, I was showing the PowerPoint, which was showing full
Let's
screen. Full
let's go
screen.
back to, maybe we should go back to the PDF because the colors
Yeah.
completely gone. And
All right. All right. I will do that. I will do that.
you can do it smaller, but it's
Yes. 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 Yeah, we can do that.
didn't preserve the color. Sorry about that.
No, no. These both are ready in hand, and so now, mm, let
Yeah,
me
this
go to
is not.
the
This is definitely. Yeah, they're
this
big.
one. I can, of course, zoom it a little. Uh,
Yeah,
is that better?
yeah, definitely. That's fine. Let's
Presentation mode, that would
presentation
be
mode.
fine.
She can't get to presentation mode. That's
Yeah.
okay.
This is. I can zoom it a little larger further if you
So
would
this
like me
this
to
is
do that.
fine. This is
Yeah.
fine. This is fine.
Yes.
Let's go to the. Okay, so let's go to the next slide. I guess your viewers probably were able to see this. Yeah, this is
Yes.
fine. This is fine. So now let's have a look at that.
Yeah, not right.
This is
We
all
have
right.
to, we have to slide down, right? We have to scroll
Yeah,
down.
no, yeah, I will do that. As I will do that. Yes.
Okay.
Okay, I would now make a synopsis of some of the astronomical observations that were made in the first 10 years of the telescope's life. As Tapasi said, the whole telescope was commissioned in 1963 for the amazingly cheap price of $10 million. One of its first accomplishments was establishing the rotation rate of the planet Mercury with its radar. It turned out to be 59 days rather than the previously estimated value of 88 days, which had been worked out by trying to identify optical features on the surface of the planet Mercury. Turned out it was very difficult to do that. It's a very cratered planet, and the optical people had not really succeeded in identifying optical features. Radar succeeded without any problems in establishing that rather than being locked on, so the same face of Mercury always faced the sun, it actually rotated 3 times for every twice Mercury went round the sun. It also participated in 1967 in this operation of very long baseline interferometry, which Jairam mentioned earlier, which Tapasi is herself a bit of an expert on, and she'll come back to a little later in the talk. And this very early work was done with the Canadians. In 1968, pulsars had just been discovered, and the Greenbank telescope, just almost outside our window here in West Virginia, an earlier telescope here had discovered pulses from the Crab Nebula, but was unable to find any periodicity within these pulses. And the Arecibo telescope managed to identify that it was an extremely fast pulsar for those days with a 33 millisecond period. And this essentially was the first clue that pulsars were left over from supernova explosions, which it was well known at that time that the Crab Nebula was the result of the supernova explosion seen by the Chinese in 1054 AD. And another big moment in the life of Arecibo was that the Department of Defense passed over the ownership to the National Science Foundation, the civil authority for running science in the USA, and its name changed from the Arecibo Ionospheric Observatory to be the National Astronomy and Ionosphere Center. And that was in 1971. It was officially renamed. Right, next slide, please. In 1972, Cornell, who had taken over the ownership of the telescope or the management for the NSF, decided they were going to upgrade the telescope, turn it into a much better instrument. And you will find one of the stories of Arecibo is that it kept reinventing itself. The surface of the 300-meter dish up to that point, good, had been made of essentially what we over here call chicken wire mesh, what you put round to keep your chickens in. Well, that's not terribly good for a high quality surface. So the surface was taken off and replaced with 38,778 perforated aluminium panels, perforated so when it rained, the water could run through them, but it made a very much more accurate surface. And an accuracy of 3 millimeters across a 305 meter diameter dish is really quite something. This meant you could work at a much higher frequency, and for reasons we'll come to later, it allowed observations at the iconic frequency of 1420 megahertz, where there is a spectral line of the neutral hydrogen atom, and that allows you to do much more exciting radio astronomy, the sort of radio astronomy that Jairam did for his PhD thesis and is still doing with the GMRT telescope in Pune. It also allowed to go up to 2.4 gigahertz, 2380 megahertz, and a new radar was installed on the telescope that allowed observations of the planets and asteroids. Could we roll down just a little, please? And the telescope never stopped observing while the new surface was put on. As one bit was removed, a new bit was put on, and a pulsar survey was done to detect new pulsars. And two observers, Joe Taylor and Russ Hulse, detected the first binary pulsar, a pulsar which was in a binary orbit together with another object, turned out to be another neutron star, just like the pulsar that they could see. And this turned out to have extremely important results, maybe even perhaps most important observation ever made with the Arecibo telescope, although there have been some pretty important ones that came after it as well. We'll come to that right away now. But first, let's have a look at this upgrade of the telescope. Over to you, I think, Tapasi.
Okay. So you see there the panels, 38,778 panels in a stack, and on the top right-hand corner, the chicken wire mesh is being replaced. So over there, you can see most of it has been replaced, and the edges are still being replaced. And go down. Here, the very last one is being put by dignitaries, of course. So I forget now who these people are. I think Cornell President must have been there, and probably some Puerto Rican politicians. So they're installing they're putting the last one in.
We certainly weren't there.
Yeah, we were not there. This was before our time. Okay, so the next one. So this made a lot of difference, as Chris explained.
Maybe I should take over that.
Yeah.
Okay, this is the paper that came out about the binary pulsar I mentioned. And you will see the title is Measurements of General Relativistic Effects in the Binary Pulsar, and then the name of the pulsar that was found. Okay, if we can roll down to the next slide, please. All will become, I hope, clear. There we are. On the left there, you will see what was going on. There were these two neutron stars going around each other, or going around their center of mass. Now, if you neglect general relativity and neglect Einstein, then they just carry on in the orbits you see there. And they are closest to each other in a predictable way. And if you time when they're closest to each other using the pulses from the pulsar you can see, then the timing should be totally predictable. It should fall along the line you see at the top of the graph on the right. Now, Einstein have said that if two very compact, heavy objects rotate around each other, a binary system, then gravitational waves should be emitted. And because of that, their orbits will precess, and the time at which they are closest to each other should change a little from the static system that I mentioned. And in fact, the two people who found the pulsar timed the time at which this closest approach happened. And indeed, they found it didn't stay constant. It didn't follow that horizontal line, but parabolically moved away from it. It's still being timed, and it's still following the prediction of Einstein's general relativity. And
Can I
you
make a
can,
comment there?
yeah,
The amazing thing is the points are the measured points, and the line and the parabolic line is not a least square fitting to the points. The curve is actually drawn from the theory of general relativity. So if you did it didn't consider what the measurements were. You draw the theoretical line, and the observation points fall right on top of that. That was amazing.
this is the most direct proof ever of Einstein's general theory of relativity. And for these measurements and for the discovery of the object that made this proof of Einstein's theory possible, Joe Taylor and Russ Holst were awarded the Nobel Prize for Physics in 1993. You can see both of them in the bottom left there. Joe having just received his medal. And in fact, the first thing he did after going to Stockholm and receive it was to have a replica, a duplicate made, which he brought to Arecibo, and to this day resides in the Museum of Science at Arecibo Observatory for everybody to be able to see and enjoy. And it was a wonderful gesture and much appreciated by staff and everybody who visits the observatory. Right, next slide, please, Ratna. Okay, another experiment that became possible thanks to the new 2.3 gigahertz radar that was installed on the telescope was for the first time mapping the surface of the planet Venus. Venus is totally covered by clouds. So up until the 1970s, we had no idea what the surface of the planet Venus looked like. Using radar and reflections from the surface of radar waves, the astronomers from Cornell were able to map the surface features of the planet Venus. They found many remarkable features. There are high mountains there. It's extremely hot on the surface. It's the hottest place on any planet in the solar system. Temperatures are enough to melt lead. There are huge mountains like Maxwell Montes that you can see on the right there is the highest mountain on Venus. There are huge plains. There are remarkable flows. It's a huge and terrifying planet. Venus may have been in mythology the gentlest of goddesses, but certainly her planet is not the gentlest of planets. And it was a complete revelation to be able to map the surface of the planet. Another example of mapping a planet that turned up a big surprise was that Mercury was always known to be the nearest planet to the sun. It was known to be, when it was the side that was facing the sun at any time, was known to be exceedingly hot. And it was a big surprise when radar mapping was made of the surface of Mercury. High reflectivity was received from the poles. And what could this be? The only thing that can explain the high reflectivity, it is a very cratered planet, as I mentioned earlier. And if you had ice in the craters at the poles of Mercury, then that would explain the high reflectivity. Ice is a great reflector of radar waves, certainly the wavelengths that were used by the radar at Arecibo. And that is possible because the rotation axis of Mercury is almost at 90 degrees to its orbital plane. And that means that the crater walls, which are quite high near the pole, means that you never get the sun shining in the craters at the poles of Mercury. So it's actually extremely shadowed and it's extremely cold, and you get water ice inside the poles at Mercury. And this was a great surprise. There was a paper published called Ice on Mercury, and our friend John Harmon, who published the paper, was quite surprised. He got a lot of reprint requests for his article, including some from chemists, which surprised him until he realized that chemists who read the article on ice on Mercury thought it was some new
Chemistry.
discovery in chemistry rather than being a planetary astronomy paper. But one can be mistaken at times. Okay, next slide, please, Radna. Okay, now I've asked Tapasi at this point, as we've mentioned VLBI a few times, if she'd just say a couple of words to explain what VLBI is.
Right. The relevance of VLBI at this point is because the telescope was at that time moved to a sort of higher frequency. It was possible to join with other standard VLBI, other telescopes to make very high resolution maps. So very briefly, what happens is this is a technique called interferometry, and in India you have the GMRT. It's a wonderful interferometer. And Jairam is a real expert in all of this. If you have ever a chance to go to visit NCRA or the telescope, please go see it and learn from all many experts there. In case of VLBI, what happens is not all the telescopes are located in the same place, and the data are not combined at the same time. But nothing is lost. They are recorded individually at each of the telescopes and then brought to a common processing center, which we call correlator, at a much later time, with various other restrictions, of course. So there's over the years, the equipment have been modernized and they are really very good at the moment. But the result we'll show you was from 1993, just before another major upgrade happened at Arecibo. But at that time, there was called that VLBI observation was really a world array where many telescopes around the world joined. For instance, here I'm showing you the map of the North America, and you see 10 telescopes there. They form a dedicated array called VLBA, very long baseline array. So there's one in the Caribbean next to Puerto Rico, not in Puerto Rico, but another island called St. Croix. So that constitutes the American array. And over to the world map, you see many red dots in Europe and right now in China and South Africa. In the image, will show you the Chinese and the South African antenna. South African one, yeah, they were not there.
So.
They were not present in that one. At the bottom, I'm showing you the some of the big dishes. So most of the VLBI antenna are smaller, relatively smaller in size. Although in Europe you have Jodrell Bank, then Effelsberg. Those are two very big antennas. They regularly take part in the European VLBI network, which is called EVN. These are all open to anybody from all over the world. People can write in proposal and get their observation done. You don't have to go there. Somebody observes for you, send you the data, and you can make very fine images of the object that you're interested in. At the bottom, I'm showing three big dishes which contribute immensely. One is a GBT, other one is Arecibo, and probably the middle one is
That's
maybe
Effelsberg.
Oh, okay. So next slide. So in 92, 93, I think 93, this image was made. At that time, you see a whole series of alphabets right at the top of this plot. That basically shows telescopes and different places. So there were about 20 telescopes that joined in, and it shows very detailed map of a radio source, and it basically shows the mechanism by which radio objects emit. So we'll talk about that a little more in a little while. All right. So at this point, Arecibo went through another big change. And now Chris will talk about that.
Okay, as I say, Arecibo kept reinventing itself, but we're on the scene at this point. We arrived in 92, and this is the second upgrade. Whole bunch of things happened. Up till then, and I'll show pictures of what happened in a moment, the surface was once again improved. It was tweaked so that we could work to higher frequencies. The antennas up to then had been things called line feeds. I'll explain in a moment. And the telescope was improved by putting a Gregorian dome, and that I'll explain, which allowed us to cover all frequencies reaching up to 10 gigahertz. And we put a whole new suite of receivers, allowing us to cover the whole band of frequencies up to then. A new radar transmitter was put on with twice the power. New drive systems were put on, allowing an active platform. The platform could be brought to a much better accuracy so that we could use the higher frequencies, and a ground screen, like a big fence was put around the telescope to stop radiation from the ground interfering with the signals and giving us much more accurate observations. Right, next slide, please, Ratna. Okay, up till 1994, I mentioned earlier that the dish was a cap of a sphere. Now, the trouble with a cap of a sphere, if you trace the rays coming from infinity bouncing off a sphere, then, as you know, if you have a parabola, they all come to a focus. If you have a sphere, on the left, you'll see they don't. They all cross at different points. And so you don't get a focus. You get a line focus. And the way that one collects the radiation then, you have to have a needle-like antenna, like you see on the right there, what we call a line feed. And you use the magic of a waveguide. The speed of light inside the waveguide is adjusted such that the rays are all brought to a common focus at the top there. And that works beautifully, but only over a very narrow range of frequencies. So you only collect a very narrow range of frequencies. So you collect spot frequencies over the band of radio waves that fall on the dish. Well, let's go to the next slide, please. And on the right there, you'll see what happens. We actually, instead of picking them all up on a line feed, we replace the line feed with a couple of reflectors, secondary and tertiary, as we call them in the top right-hand picture there, which re-images those rays and brings them to a common focus on the left there. And you can see it in 3 dimensions on the left. And that is totally achromatic. So any frequency will then be brought to that common focus. So we've done away with the line feeds. We've done away with the problem of only having narrow bands. And anywhere from, it turns out, about 1 meter wavelength down to about 3 centimeter wavelength, from 300 megahertz wavelength to 10 gigahertz wavelength, you can, in fact, work just from a single point focus inside the dome. Next one, please. I should perhaps say a little more that Tapasi mentioned earlier about how we point the telescope. You'll see the dome sitting on the azimuth arm on the top picture there. And if you look at, well, there's a typical pair of optical telescopes bottom left. Normally, an amateur telescope will be mounted equatorially. That is, you'll mount it depending on the latitude you're observing at, and you will swing about a mounted at the angle of your latitude, so that as you swing it, it will follow a star. But it can also be altaz, so you will have to move it in 2 dimensions. Well, the Arecibo telescope was in fact an altazimuth telescope, plain and simple. It could rotate on that ring hung from the platform, and that is an azimuth movement. And it can also move up and down the azimuth arm, and that is a movement in elevation, or zenith angle as we usually prefer to call it. And you have a computer driving it in those 2 dimensions, and it can follow a star for about plus or minus an hour and a half. So it was quite capable of following a star, and the astronomer didn't need to know about the drive. It was all done for him or her by the computer. Right, next slide, please. That was the raising of the dome.
Yeah, the dome was constructed at the bottom of the dish on a platform, and then on the morning of May 16th, it was raised. And the dish was at that time full of mist, and it was really lovely. Sorry I interjected, but it brings up such beautiful memory. It was early morning, and dome kind of winched up. It was lifted on a winch up there, and then attached to the azimuth arm. Carry on.
Right. Okay, next slide, please.
No, Nick, was it next slide?
Yep. This is what it looked like inside the Gregorian dome. You had a secondary reflector which covered the inside of the dome. That was the one I showed in the diagram earlier. And that reflected down into the tertiary reflector, which is at the bottom middle of
it's looking like a basket. Yeah, you're looking at the back side of it. It's looking like a basket.
And we, in fact, ran out of money right at the end of the project. So the astronomy department assembled the tertiary reflector. Tapasi and I and all the astronomy department got our sleeves rolled up and put the tertiary reflector together. And above the tertiary reflector, you can see what is effectively a 2-story building. And if you go to the next slide, that's inside the lower level, which is all the receivers. And they're actually on a rotary floor. And you can rotate that floor to bring any one of the receivers which cover a band of frequencies to the focus, which is at the front of that, to the left-hand side of that picture. And you could change to bring any band of frequencies into play within 1 minute. It was amazingly frequency agile, shall I call it. And if you go to the next slide, that shows the room above, which is where the radar receiver or radar transmitter, I should say.
How much power?
And that was about a megawatt of power, which could be transmitted out into space to intercept an asteroid or a planet, and would then be picked up with the appropriate receiver on the floor below. Okay, next slide, please.
Oh, no, that's the final.
Oh, that's the final fully assembled, reinvented Arecibo in 1998, all ready to start work again. Okay, next slide, please.
This is a very quickly we'll go over. This is a list of the receivers. Yeah, we just focus on the top box, and at the when the telescope was just with chicken wire mesh, it was the first two bars, like the pink and the green on the left hand side. Only that much of frequency was covered, and after the surface was changed, it went up to the pink, which is considered S low, written as S low. Only up to that was covered at the second upgrade. And with the Gregorian upgrade, it was all the way to the X band of 10 gigahertz. And it was really a frequency agile telescope with the biggest collecting area. and that made many things possible. Next slide. Okay, yeah, I think, yeah, we were mentioning the radar astronomy. Neither, both Chris and I don't do radar astronomy, but we'll just try to explain very quickly. What happens is, this is in radar astronomy. You probably know that using radar, people tracked airplanes or ship on the ocean, right? So how it works is, you shoot out a radar beam to a far off object, and it then reflects back, and you get the reflection or the radar echo back. And when you record that, because of Doppler motion, or some uh, the frequency where you receive this radar changes, and that could happen because of the object moving as a whole, or object rotating, and also how far the object is. It will determine how much time later you get the reception back after you have transmitted. So this is called delay Doppler mapping. Here what we're showing is, the radar was shot out, say, with blue traces, and then they get reflected from the far off object, and then the red traces
Red goes out, blue comes back.
red went out, and then the blue comes back, and then that gets into your receiving system. And using this delayed Doppler tracking method, you can basically map the object. You can measure its size. You can measure its orbit very accurately. You can also measure its rotating period, and you can also study what kind of object this is by measuring other quantities like polarization. We won't go into the detail, but you can measure the orbit of the object. You can measure some compositional character, whether it's a binary, tertiary, or some other things. So you can determine a lot of information very, very accurately without sending a spacecraft. Okay, just from the ground, it's a lot cheaper way of measuring such things. So let's look at the next slide, please.
Right, shall I do that one?
Yeah. Okay.
Okay. Some example of some near-Earth asteroids which Arecibo has imaged over the last 20 years. And in fact, we always think of Arecibo as guardians of the Earth against potentially hazardous asteroids. All these are asteroids that have passed close to the Earth, meaning either, should we say, fairly close to moon distances, or several times moon distances, but not at the distance of Mars or anything like the main asteroid belt, but near enough to make one a little bit concerned that they are potentially hazardous to Earth. These are, first of all, JM8 is a number of images made one after the other, and you can see it's rotating significantly, and you can get a number of images of it as it rotates and get an idea of its three-dimensional aspect. If we take the one below that, could we move up? Thank you. That was actually one of the last asteroid images Arecibo made before its tragic collapse. 2020, so that's the year, BX12. And you will see the main asteroid is the large object. These are two images, and you'll see there's a small object. This is an asteroid that has its own moon, and that is a point to remember with potentially hazardous asteroids. You may get missed by the big asteroid, and when I say big, these may be a few hundred meters across, but they can have their own moon. So you have to make sure not only do you not get run into by the main asteroid, you have to be sure you don't get run into by its moon as well.
And these were not known before Arecibo images at all, that asteroids could be binary or triple objects. that was not known at all.
Yep. Really, there were only two telescopes that were able to image asteroids, and Arecibo was one, and the other is the Goldstone antenna in California, which is only a 70-meter antenna. So Arecibo was pretty unique.
These two.
Could we go to the top
Right.
right-hand image there, please? No, back, previous image. There we are. Now that one is even more, whoops, there we are. That's even more remarkable in that it's a triple asteroid. The asteroid has two moons of its own, two small moons. And you can see that while that image was being made, both the moons have moved significantly in their orbits around the main asteroid. They look like little streaks. So sometimes you have to even not just watch out for the moon, look out for the
Where they're
moons.
going. Yeah. Next one.
Okay, and the one below it, this is an amusing one. It got called spooky because it looks a bit like a skull. And the funny thing was that it was detected on Halloween night when all things spooky are supposed to happen. And the radar group at Arecibo were highly amused by this. I suspect they massaged the image a little to bring out its spookiness to its maximum ability. Anyway, that's the sort of thing that Arecibo were doing. It must have imaged well over 100 near-Earth asteroids over the past 20 years. And sadly, it's not doing that anymore.
Yeah. Can I add one quick about asteroid? That knowing the composition is very important because they always talk about how to mitigate it. If an asteroid is known to be coming towards Earth, what can we do? So if you know the composition, maybe it will be easier to plan how to deflect it. A current solution is slightly deflected from its path if you know it already where it's going. So knowing the composition, knowing where it is going, all these are very important information.
And one thing we should add is that Arecibo not only could image these, but they could measure exquisitely accurately their orbits. So they could predict the future of these asteroids and whether they really were hazardous to the Earth.
And Arecibo couldn't do all ones. There were optical telescopes that continuously watch them and then produce a list of asteroids. Even now they're doing that. The ones that were visible from Arecibo's telescopes, those had the chance of further study by this. Okay, next slide. Okay, so
This is your
back
baby.
to all of us back to an astronomy example of the upgrade telescope. These are all examples. There are many wonderful research had happened because of this upgrade. We're just showing a few examples that either we know of or we were involved in. Okay, this is finding a molecule that's called the prebiotic molecule in a far-off galaxy. This galaxy's name is ARP220. It's a so-called it's a hugely fast star forming galaxy, so it's forming star at much higher rate. It's a result of two galaxies merging together, so there's a lot of things happening in these galaxies. So we were actually many whole radio astronomy group as well as the person who programmed this equipment, we all wanted to test the equipment. So we decided we will do one common project to test out the equipment. So we pointed at R220 and we scanned through all the frequencies to take spectra of them. And up came this wonderful spectrum. We didn't know what it is, so what it was. So we then searched what it could be, and by trial and error, you rule out other things, and then you find that this is supposed to be a molecule called methanamine. Its formula is CH2NH, and it so happens that it is a so-called prebiotic molecule. If you combine this with hydrogen cyanide and water, then at the end you can produce one of the simplest amino acids called glycine. So that is finding, and amino acids are 20 amino acids make up all proteins on Earth. So or all proteins on human body, I think. or all proteins on Earth. I'm not quite sure.
It's me. I'm no
So there are
biologist.
20 amino acids. Those are vital for proteins. So glycine is the simplest form of that. So we found that, and that was a huge, exciting thing. Later on, we observed many other sources, and about 4 of similar type galaxies also showed similar molecules. So these wouldn't have been possible without the upgrade. And research was going on, and then, of course, it had stopped. All right, next slide.
This is you as well.
Oh, okay. So I mentioned VLBI earlier, where all the telescopes you saw were on Earth, but but then there were other big step in VLBI where they put antennas in space. The one on the left hand side was from a Japanese telescope called VSOP. It ran from 1999 to 2001. Just then, Arecibo's upgrade was complete, and it worked at 327 megahertz and L and 1.4 and
Gigahertz.
5 gigahertz and 22 gigahertz. Arecibo couldn't do 22 gigahertz, but other three frequencies. And one interesting point here, an Indian connection, a very dear friend and TIFR engineer, Alexander Praveen Kumar, who's probably retired now. He made the 327 receiver, which flew on that no, which flew with the right hand side on the Radio Astronomy mission. So one on the right hand is a Russian mission which went up in 2012 and worked till
Last year.
2018,
Well,
2018 or
yeah.
2019 almost. So that exceeded all expectation, and Arecibo took part in all of these observations, producing very high frequency, high resolution images. And talking about resolution, you might hear words like milli-arc second, which is a thousandth of one second of our angle, 1 arc second. It is like if you take a 1 rupee coin and hold it up in Delhi, and you can still see its disk from, say, Chris's home in London. So that will give you the amount of resolution power that these telescopes combined with telescopes on Earth gave us. Okay, next slide, please. Okay, this is another upgrade that happened at Arecibo. Chris is going to talk about that.
Okay. This isn't a telescope upgrade, it's an instrument upgrade, but in a way it was like the third upgrade of the telescope. It was our introduction of a radio camera to Arecibo. It's a device called Alpha, the Arecibo L-band feed array. It was built in Australia, and instead of just looking at one place in the sky, it allowed us to look at 7 places in the sky. We call it a 7-beam receiver, all working at the same frequency, but it meant you could literally snap a 7 pixel picture on the sky, like a very crude camera. And bottom right, there's a picture of one region of the sky. The picture on the left is the optical picture of it, and the picture on the right is the radio picture. The two at the bottom I won't go into there.
Mm-hmm. Can I mention one thing?
Yes.
This receiver was actually built in Australia, and it was bought and brought in to be commissioned, to be put in the Gregorian dome of Arecibo. So Arecibo did not build it; it was built in Australia.
Yeah.
Okay. Next.
Okay.
Next slide.
Next slide, please. Now, just going to mention a couple of the reasons why, of what we do with, or what we did with Alpha. Tapasi, you were going to, I think.
Oh, okay. Yeah, so there are a very brief introduction to natural ways the radiation is produced. There are many different ways here. We mentioned only 2 methods. That was basically at the back of the results that we are going to show for coming from Alpha. So first one is a spectral line transition of neutral hydrogen. What happens is hydrogen, as you might know, is made up of proton and a neutron. So
Electron.
sorry, proton and electron. Sorry, if you had proton and neutron, you get deuterium. Sorry, proton in the nucleus and an electron in the orbit. So if those two are aligned in the same direction, they're spinning in the same direction, they are at a higher energy state. And if they're anti-parallel, the proton spinning one way and the electron spinning the other way, they are in anti-parallel mode. That's it. That's the basically the ground state. And spontaneously, they should decay from the higher state to the lower state. The probability of that is low, but in the whole universe, there's just so many hydrogen atoms that even though probability of individual atom doing this is low, but there's so many atoms that we have detectable neutral hydrogen transition. And that when it jumps from the high energy to the lower energy state, it emits a radiation at 21 centimeter, which is 1.4, near about 1.4 gigahertz. And using that line, because it's a specific line, you can study a lot of things. Because if the emitting gas is moving, that line gets either broadened, it gets redshifted, it gets blue shifted by the line's frequency where you observe it. By the width of the line, you can study many things. So here is a picture, an example picture, all sky, 21 centimeter. This is showing our galaxy, how it glows up in neutral hydrogen. There are stars, of course, in all over our galaxies, but there's this bathed with neutral hydrogen gas. So the colored image is showing that. At one point, if you take a spectral profile, it looks like this. Right at that point, in a different point, it will look different. It basically shows the spiral arms of the galaxy. So a lot to learn from that. So the picture on the right hand side, the graph on the right hand side shows an example of how radio radiation can come, which will not be a line radiation, but it will have power at many frequencies. Hence, it's called a continuum radio emission. So it's emitted by a process called synchrotron emission, where very high energy electrons, if they're moving in a magnetic field, high relativistic electron, if you put them in a magnetic field, what happens is, because of the electromagnetic interaction there, it feels a force that makes their trajectory spiral. So as they move in spiral motion around the magnetic field, the spiral motion is basically accelerated motion because it's changing its direction of velocity. So it will emit radiation, and this radiation is also beamed, and but that direction is changing always. So there's a whole lot of uh, mathematics worked out due to that. If you have a bunch of electrons all with different starting energy, put them in a magnetic field, what you get is radiation at a very distributed frequency range, which is called continuum radiation. Using that, you can study objects that are very special. I mean, it's very strong in radio emission, radio region, and it is also it has a very specific signature, which is linear polarization. I'm using a lot of jargons here, but sometimes you can't avoid jargon. As you learn more, you will get used to these terms. So over to Chris.
I always find it intriguing that if our eyes were radio eyes, then the sky would be bright at night due to synchrotron radiation, that the sky would be lit up by these cosmic ray electrons, at least at low frequencies.
Yeah.
Right.
Okay.
Could we go on to the next slide, please, Ratna? Okay, now just going to very quickly mention some of the science that was made possible by this alpha camera. One of the groups, we invited the scientists of the world to come together and form consortia to exploit most productively the alpha receiver. And one of the groups that did were the extragalactic people interested in studying H1 from galaxies outside our own Milky Way. And they devised what they called a wedding cake approach, where you can see an American wedding cake on the left, which comes in 3 tiers, a big one, a middle one, and a little one on top. And they did that. The big one is an experiment called Alfalfa, which did a wide area, shallow survey covering almost all the sky away from the galactic plane available at Arecibo. And they used alpha to look over the whole sky, detecting galaxies by their H1 emission alone, wherever they could detect a galaxy. And they detected 31,500 galaxies purely by their H1 emission, out to a redshift, well, quite considerable, 0.06. It's a reasonable redshift. Shall we say they mapped the whole local and not so local extragalactic space. Then they plotted it on plotted the galaxies they detected, and in that fact found that the galaxy lay on filaments across the sky, and mapped out these filaments and into what they call the cosmic local galaxy web. A second experiment detected H1 emission in galaxies laying in different environments, from rich galaxy clusters within that web down to voids, seeing if they could find galaxies where there hadn't previously been known to be any galaxies at all, where it looked like voids. And in fact, they found galaxies even within the voids, and mapped right through the spectrum to rich clusters, finding low brightness, but still quite rich H1 neutral hydrogen containing galaxies. And then finally, a group called the Ultra Deep spent 700 hours mapping down to the weakest H1. When I say H1, I mean neutral hydrogen, detected galaxies in just a square degree of sky. And I've put there the spectra they detected on the right-hand side there. And those are amongst the weakest H1 detections ever made from galaxies detected at random. Then below that, the pulsar people did pulsar detections on the galactic plane. These are objects very much in our galaxy. They searched for pulsars at low galactic latitudes, where you expect pulsars. They detected 196 new pulsars. These look very much like the spectra above them, except that here, this is the characteristic pulsar profiles. So here they're not against frequency, but the profiles against time. And many of these are millisecond pulsars. The Crab pulsar I mentioned earlier had a period of 33 milliseconds. These are ones with pulsar periods of just a few milliseconds, much faster even than the Crab. But 196 new pulsars, and that data is still being looked at, and new pulsars are still turning up from it. Okay, next slide, please. Okay, now the people who are interested in H1 in our own galaxy, neutral hydrogen, weren't to be outdone. They mapped the neutral hydrogen in our own galaxy. There's some pictures of H1 in our own galaxy. They found that the neutral hydrogen in our galaxy is not smoothly distributed, but distributed in long filaments.
Yeah.
And those filaments stretched along the magnetic field that is found optically from the dust alignments of grains in our own galaxy. And so that was an extremely interesting discovery, and one that's being exploited very much at the minute.
Can I mention one thing there? The aspect ratio of these very thin neutral hydrogen sheets are almost like a A4 size paper, their aspect ratio. they're hugely like a parsec, like
100 to 1.
yeah, but they're huge in size, but their aspect ratio is like a A4 paper, but they're like parsec size, long, big.
Yep.
So they're amazing, and they're now studying combining Sophia, which is like imaging the dust, etc. A lot of research going on in this area.
Yep. The continuum people, which include ourselves, were not to be outdone. So if we can roll down to the bottom of that slide, please.
Yeah.
I'll particularly point out the top picture, which is a picture of the synchrotron emission from the galactic plane. You will see the Milky Way in the middle marked I, and there is the Milky Way itself, much brighter than we see it with our optical eyes, running diagonally across the picture. And you can see an object going up from the middle of the picture, from middle bottom to top right. That's an object called the North Polar Spur, which is thought probably to be a local supernova remnant that went off something like 100,000 years ago, and is seen only in the radio. And the bottom two pictures actually are what the polarized emission from the synchrotron radiation look like, but I won't dwell on that. Other surveys have taken place with alpha. I won't dwell on those now, but for things like looking through the galactic plane, which is obscured to our optical eyes, looking for galaxies by their H1 emission behind it, and also for something called recombination lines, which Jairam knows all about, which is the recombination at higher levels of hydrogen atoms. Right, next slide, please. We're getting near the end now. Tapasi particularly asked me to put this one in, and she also asked me to talk about it. Interesting objects were found about 15 years ago called fast radio bursts. These were mysterious single bursts of radio radiation that turned out to be coming from way outside our own galaxy, of enormous power, but just single bursts for many years. Then Arecibo showed that one of them at least was a repeater. It didn't repeat very often, but every about 190, I think, days, you would get a burst of repeating.
But not very regularly, like a pulsar, but they will show up again.
Yeah. And since then, other repeaters have been found, particularly by a telescope in Canada. Anyway, the original repeater that Arecibo showed to be repeating, a VLBI experiment was done where one studied the place where that repeater was in the hope that it would give a flash while we were recording VLBI data, and we could locate down where it was. Well, it turned out it did give a flash, and we were able to locate it down to a very insignificant galaxy, a dwarf galaxy. Yeah. And this dwarf galaxy had another radio source within it, which is presumably its own nucleus. And this flash came from near the nucleus. The object you can see, the one in the middle there, slightly brighter one, is the nucleus. The white cross is the repeating fast radio burst, and you can see it lays very close to the nucleus of that galaxy. These objects, it's still not known what these objects are, but it's very likely that it's related to another set of objects called magnetars, which are extremely highly magnetized pulsars. And They are mysterious objects, but Arecibo has added a lot. Tapasi wants to say something.
No, no, not on that. The next.
The next slide, I think.
Okay. So then quickly, other notable contribution. I mean, there have been so many, we're probably not doing justice to the breadth of science that has, it's still going to come out because people have acquired data. But we'll note two different things here. In 1992, the first exosolar planet, was found by Dr. Alex Olshan of Penn State University. And this was planet around pulsar. So that was really intriguing. Before all the other exosolar planets were found, way before, Alex found these pulsars containing planets in their with them. That was fantastic.
I would add there that I don't
this
know.
is a stamp.
Alex may not have got a Nobel Prize, but he did get recognized by his native country of Poland by being put on a postage stamp.
And the person behind is Copernicus. Nicholas Copernicus is at the back and Alex at the front. Okay. So, and then this is another work which is probably going to have a huge impact. They are very close to detecting long wavelength gravitational wave. This is a consortium that is called NanoGrav, and they have been observing timing millisecond pulsar. I know people in India are also doing LIGO related work to detect gravitational wave. This is another way of detecting gravitational wave. This is a topic on its own, and I haven't done anything there. I'm not an expert, but I'm sure a lot of people can talk about it. Two major telescopes, Arecibo on the left and Green Bank on the right, are huge contributor to nanograv observation. So Arecibo collapse is a big blow to the whole nanograv, although they still have 2 more years of data to be processed. When all of that is done, they expect to have some detection. So these are the two major work that are going to come out. People also have loads and loads of data taken on various important projects, which I'm sure in the next 5 to 10 years we will see all those work come out. All right.
Okay, and on to the last slide, I think.
Mm-hmm.
The very sad slide, difficult times in the future. The last 2 or 3 years have been difficult, and the last 3 months have been incredibly difficult. That is not a spiral galaxy on the left there. That is the Hurricane Maria, which struck Puerto Rico in September of 2017. It was a Category 4 or 5 hurricane, the biggest one to strike in 100 years. It says there with winds up to 15 miles an hour. That's because I have a sticky key on my computer. It should say up to 150 miles an hour. And 85 centimeters of rain fell on us in 24 hours. Tapasi and I survived through that in our house, and it was the most terrifying experience of my life. The next piece says, serious damage to the observatory, but the observatory was back on the air within a very short time, as I remember it, a couple of weeks. There was damage, but we were back on the air at the lower frequencies within a very short time. At the beginning of this year, then, a sequence of hundreds of earthquakes, never before known, up to magnitude 6.4, struck the south of the island, and whether that contributed to the disasters later in the year is still not yet confirmed. Time will tell, and forensic studies are being made of the disaster that happened. But on the 10th of August last year, an auxiliary cable to the platform fell, and observations were shut down just after, in fact, a beautiful detection of the OH molecule from comet Neowise, which many of you may have seen from India. And they were just about to make a second observation to study how the molecule was changing when that cable fell, and it was never made. Then a main cable to the platform broke on the 6th of December, and on the 1st of December, and I'm afraid I have to show that picture at the top right of this slide, the whole platform came down. Tapasi and I have not yet been able to bring ourselves to see the video of it happening, although I believe videos are available, but please don't ask us to see it. As Jairam and Ratna said, it's like losing a family member. The folks at Arecibo, led by Anish Roshi, head of astronomy there, there's a large number of Indian scientists at Arecibo. P.K. Manoharan, who many of you may know, is there. There are members of the planetary group, members of the astronomy group, young Indian astronomers there as well.
And Anish Roshi.
Anish Roshi, I mentioned, yeah. They have very quickly put together a design study to replace, as I say, the old warhorse with the next generation Arecibo telescope. It's still a design study. It's been submitted to the National Science Foundation, and I can't remember exactly how many, but a large number of endorsements have been received from the global science community, and it is still open for endorsements. If anyone listening today wishes to log on and endorse the next generation Arecibo telescope, then I know they would be extremely grateful. But please keep logging in and see how the prospects for the future go. Certainly, we are hoping that the wonderful work that Arecibo has done in the past will be recommenced and carried on into the future with a new generation of global scientists. But thank you so much for listening today.
And thank you for giving us the opportunity to talk to you. And thank you, Ratna, and thank you, Jairam. You are our dear friends for so many years.
Absolutely.
And wish we could go and personally give this talk or other talks and talk to all of you. But one of these days, hopefully that will happen.
Yep.
Thank you so much for putting us and the viewers in picture about this 5 decades of work from the observatory. Jairam?
Yeah, no, I don't have, I'd just like to thank both Chris and Tapasi again for, this very comprehensive, over the years look at, the science done by the telescope and the telescope itself. And, I can't but help notice it was also in the grand tradition of cricket commentary, with one taking of the other.
I haven't seen the score today, but I think I last saw it. As an Englishman, I shouldn't be too interested.
Yes, they did not do well, Chris. I'm sorry to tell you.
I'm a West Indies supporter.
To all the viewers, please do the endorsement which has been discussed here. There are some questions. I'm flashing them here from the viewers. My eyesight is not too good to read this. Let me just see.
But maybe I could then just read them out. Maybe I'll read them in the order that I see them. The first question was, can one do radio science at low frequencies with Arecibo? Could one, I guess. Sadly enough, now it has to be phrased in the past. Yeah.
By low frequency, what do you mean is the question, because a really ultimate low cutoff is about 10 megahertz, because below that, it won't, the radio waves from space will not penetrate our atmosphere to come down.
Let's talk in terms of the telescope as it was modified with the Gregorian dome. The lowest frequency it could work at was 300 megahertz because of the size of the pupil that the radio waves went through to get into the dome. If it was lower than 300 megahertz, then the pupil was not enough wavelengths across to allow the radio waves through. But 300 megahertz was a standard frequency we used for VLBI, for pulsars. Tapasi and I have done looked for high redshift H1 absorption at 300 megahertz. At one point we used an 800 megahertz receiver when one trouble at low frequencies is radio frequency interference. But very conveniently, at one time, the US decided to move all its TV transmitters in the 800 megahertz band, 700 to 800 megahertz, up to digital transmissions at higher frequencies. And for 3 years, the 700 to 800 megahertz band was clean. So very quickly, we put together a cooled receiver on that band, and for 3 years made spectral line and continuum and pulsar observations in that band. And in fact, we made some H1 absorption detections of high redshifted galaxies, quasars and radio sources in that band. So yes, but our pulsar people have detected pulsars down at 44 megahertz. Which is
there's the
low.
other carriage house on the other side that had a 47 megahertz receiver. That wasn't used very much because of the interference. It sits in the middle of the TV bands, so it was difficult to use it. But people tried, and there were a special observation at 120 redshifted hydrogen. There was one person tried by adding extra feed, so people could bring in their own receiver and technically try out something, and people did try it. It wasn't the standard way of operating.
As you will remember, Jairam, Arecibo prided itself on people bringing their equipment.
Yes, I do. Yeah.
And that applied to a number of people arriving with their own
Feeds. Yeah,
noise
hanging from the catwalk.
Yes. I remember that. Yeah. The next question is, a request to explain a little bit more about the Gregorian dome and how it was used.
Yeah. The Gregorian dome was used by all of the three groups of scientists who work at Arecibo. The astronomers, of course, were the prime gainers because we could then operate up to 10 gigahertz. For the first time, we were able to do extensive molecular line observations. The improved surface of the dish, coupled with the higher frequencies, meant that the radar people got much higher efficiencies for observing the planets and asteroids. But the astronomers studying the atmosphere were able to get much better observations because they had a 430 megahertz radar within the dome of the telescope, but they also had the existing line feed still on the other side, so they could look in opposite directions at the same time, and they could study two different directions at once and get motions within the atmosphere by studying opposite directions.
Yeah, the upper atmosphere's velocity vector they could find the plasma block. But if you want us to describe the Gregorian dome a little bit more, is it possible to go to the picture there, or shall we? Because all the receivers were inside this dome. Okay, So major receivers, yeah, if you go back to one of the pictures, let's see which one. Keep going back a little more here. Yeah, so no, so okay, let's go one more. Go down, go down. Yeah, let's stay here. All that you see here is inside the dome. The dome is a huge construction. Okay, the white shiny thing that is facing us, which is inside the Gregorian dome written on top, that is the secondary reflector. Okay, and that reflector is a 25-meter antenna. It's like a VLA dish looking down. Okay, looking down. And down below, if you move it up a little bit, we can see the opening. Yeah, at the bottom left hand corner, you see the edge of the dome's pupil.
That is the pupil.
That is the pupil. So radio wave from the sky come and fall onto the primary reflector, the big dish, and then they come to a focal point,
come
through this hole, fall onto the big secondary reflector that is facing you here, top left. Then they come again, get more concentrated, and fall onto the inner surface of this basket-looking thing, which is the third mirror. After that, they come to a focal point, which is just above to the right. And just above to the right, you would be able to,
perfect.
those are the feed horns, the opening of the horn, which is collecting the radiation.
That is the bottom of the rotary floor.
And the electronics and all of that are inside a housing that is sitting on top of those feed horns.
We can go down 2 slides. We will see the receivers.
Yeah, this receiver room is sitting on top of
back up one if we could.
Yeah, this receiver room, the floor of that is what we were looking at from the previous slide. That one point on this floor is the focal point, and this whole floor is rotating. So the whole floor is not in focus at this moment. Only one point in this whole floor is the focal point, but you can rotate the floor to bring any receiver onto the focal point.
And in fact, each receiver shares, for those who are technically minded, each receiver shares an intermediate frequency.
That is
and the intermediate frequency cabinet is in the middle of the rotary floor.
You can see all kinds of electronics sitting around the center, and the the things that look like tube, those are the vacuum tubes, which is basically keeping the whole thing in cool. And then the electronic that is doing the first frequency conversion here. And then that IF, that signal is brought on fiber optics all the way, fiber optic cable comes out of this room and walks about a mile over the catwalk, down the side of the hill, comes into the control building. That is where further electronic massaging happens. And then it goes into the recorder.
You can see the control building probably in that picture.
Yeah, we didn't show any picture of the control room. That is a shortcoming of these slides.
Maybe if I could just add that the Gregorian dome also serves the purpose of protecting that secondary reflector from wind loading and from rain falling into the tertiary. Otherwise it would be like a sail, right? It would be the sail that you put up high in the air, and if it caught the wind, it would literally get blown away. So you need to protect all of that from wind loading and also from rain filling up into things. So that geodesic dome does that.
The secondary reflector is actually very thin. So that's a very important point.
Yeah. And so the next question, I think, is actually a good opportunity to talk about, an important role that Arecibo has played over the years, which is about Arecibo and SETI.
Yes, we should have mentioned that, shouldn't
Yeah, we
we? Yeah, there's been a number of SETI observations, none of which Taposhi and I were involved with.
we've seen
We've
people,
had
and
seen
they're
them,
good friends.
and in fact, the SETI people have used our signals. One thing we didn't mention is that Arecibo has led the way of what is called commensal observing, which is doing more than one experiment at a time. That this can be very often astronomical observations, that you can be observing, say, a continuum survey, and part of your signal will go to searching for pulsars at the same time.
Katie worked in that
Yeah,
mode quite a lot. So anybody who was, anytime the one particular receiver was in focus, they would take that signal, put it through their data processing system, and look for signature of that had signs of extraterrestrial intelligence. So look for
Wo-
some
of
Would
course.
it be would it be okay to say that through these efforts, um, even without our direct detection, it has been possible to say that our near celestial neighborhood is not teeming with extraterrestrial life. That has been established through this.
I mean, at least with extraterrestrial life,
yes,
which is technologically developed and
That
exactly.
much has been established.
Yeah,
yeah.
we may have bacteria somewhere, maybe on Mars, but yeah, not that we have detected any. But SETI had been looking at signals. They have had dedicated observation right at the beginning, and they brought in their whole equipment. They actually donated a receiver to Arecibo at one point, and they got some observing time in
Two
exchange.
receivers.
So they have been good partners in many ways. They have helped with the
Yeah.
technology. They developed a lot of technology. And SETI at Home program that a lot of people in the early days downloaded onto their home PCs, and they got data from Berkeley, but data actually came from our Arecibo telescope. That was this data taken in commensal mode when
May
this
still
was
be
taken.
going on for a
It
while.
may still be going on. So, well, now there's no data collection, but the old data turning through their processing. So they have millions and millions of channels. What Arecibo had not done is breakthrough program that people might have heard of, which was started by a Russian oligarch, Yuri Milner. He also gives breakthrough prizes. He does a huge amount of search. Arecibo had not taken part in that because of some
Yeah.
I noticed somebody put up a question earlier. What is the furthest back that? There we
what's
are.
the maximum distance?
I have no idea in terms of light years. I guess I have actually. Certainly, the furthest detection Taposhi and I have made, I think, was the H1 absorption in CTA 21.
Well, that's a line, but
That's a
we had
line,
the
but that is together
quasars going
with
so far. Oh,
with an NCRA astronomer, DJ Saikia, and that is back to about half the time to the Big Bang. So that would be back about 7 billion light years.
I think this question is also needs to be a little more specific, because sometimes how far you can detect depends on your how sensitive you are. Because as far as you go, your detection, the amount of signal you get becomes weaker and weaker. Okay, so in if you can integrate, if you can stare at one point very long for a very long time, and then you can detect fainter and fainter objects that could translate to farther and farther objects. So this question is not very straightforward to answer, to say the least. I mean, would you agree to that? Like, what do you think,
Well,
Jairam?
of course, you're all the time you're detecting the cosmic microwave background. 3 degrees
So
K is everywhere, and that's
absolutely. So
Yeah,
it
yeah.
is.
No, I
It's
agree. It's
quite.
not a straightforward question to answer. Yeah, yeah. But I did want to, I mean, just seeing the photo in the background, if you all don't mind, I just wanted to point out another connection to India, which is with the ground screen that you see over there. If you
Oh
look,
yes, we forgot to
if you look
mention.
around the dish, there's this screen which Chris and Tapashi referred to earlier. Maybe I don't know if somebody could just point to it with their cursor. Is my cursor visible? Mine may not be. Yeah.
No,
No, no, cursor is not visible over these.
Yeah, yeah. So, but you can see this fence-like thing over there, and it serves a purpose of sort of making the telescope slightly more sensitive because
lot of lots.
it protects the receiver on the top from hot radiation which comes from the ground. And that all of the material for that mesh was actually produced by the same vendor who made things for the GMRT. The GMRT needed this mesh, and so this person had set up a sort of a fabrication yard to produce it. And around the same time was when Arecibo also wanted the same kind of mesh, and so they got in touch with Govind. Govind put them in touch with this vendor, and he supplied this mesh, which is a little bit of made in India, sitting in Puerto Rico.
Absolutely.
completely true.
And
I remember it getting dropped off at the dock at
Arecibo.
Arecibo. Yeah.
And actually, the way we heard is it was Gavin who told Mike Davis that
Yes.
he could supply that.
Mm.
If they had to buy American stainless steel, the cost would have been 10 times more, if not
And
more.
if it had been aluminium, it would have had to be replaced every
Every
7 or 8 years.
yeah,
Yeah, yeah.
Indian stainless steel is sitting right there.
Yep. And it would have lasted for another 57 years.
Yes.
So thank you to uh, Chris, Tapushi, and Jairam. And thank you to Priya, who is also there in the background helping us, and to all of you who have been present with us live. I was a little disappointed not to see very heavy live presence. I mean, not very low live presence really, but it will pick up viewership in recorded version, I think. And if there are questions anybody would like to ask after seeing the recorded version too, they can be placed, and I'll pass them on to Chris and Tapushi and Jairam. If anybody would like to have any other questions answered later, those who would be seeing it. Thank you so much for this. I will be ending the broadcast now if I don't see any further questions coming in, and we may perhaps have continuing discussions with specific areas which have been looked at and so on in this connection.